Okay, and it's not been terribly long. You guys, many of you may even have the book this came from. This is the one that Miller and Allery, the swine nutrition book. And this was a quote of Picus where he said that it's difficult to distinguish between digestion and absorption. That was in 91. Today we're talking about lots more complicated things than that. If you're truly into trace elements, you're not just looking at one or two things, but transport proteins, receptors, binding proteins, things that we don't talk about much in swine nutrition, but maybe we should, because it makes a difference as to whether the animal needs a certain amount or whether it's in excess. And we know, as we were challenged earlier, that's the dollars and cents that we have to make for our producers right now. I know you can't see this because I sat in the back of the room. I can only, even if you use the little things, I know you can't see. So I'll try to go at least a little bit fast on this. I got rolling in here the zinc and copper SOD. The reason I'm bringing this part in here first is I'm going to do a little biochemistry. You guys don't go to sleep. But the reason I'm bringing it in is for us to see the metabolic needs we have. You know, just putting it in the liver doesn't meet any metabolic need. It is called storage. So we need to be thinking more in terms about what does the animal actually need. So I had to do a little biochemistry here. We have to, the zinc and copper SOD, the enzyme gets rid of the superoxide radicals. And I'll try to pull through this kind of fast here. We know we also have superoxide radicals that come into the mitochondria. And the manganese SOD, okay, you getting the picture? The minerals are kind of important here. You guys know my bias. Anyhow, and if we keep looking here, we will find out that glutathione peroxidase, pardon me? I take the phones away from kids. Now you guys don't go back and tell that they took the phone away from me. Embarrassing. In zinc absorption, there's a few facts we're fairly sure about. And I'm going to go through these in words, and then I'm going to show you an illustration if we can see it. We're going to hydrolyze the zinc, and it's going to occur in the stomach or the small intestine from the amino acids, from the nucleic acids. Most of the absorption is going to occur in the proximal small intestine. Do not look at these things where people are looking at the cecum or the ileum and talking about absorption. The amount that it does is teensy compared to where it really happens, which is the first part of our small intestine. Pharmacological zinc, however, plays havoc with all the systems because we overwhelm the typical control mechanisms, and it can be absorbed both as a passive means of absorption or what they call paracellular, where it will go in between. If we look at, we know this, gosh, this is ancient history. People like my major professor, who was Dr. Miller, lots of other people did the work where they showed the things like, I always think about the Odell papers. Now that tells how old I am, but anyhow, whoops. The phytate, and it's interesting because phytate is not always just phytate. There's different kinds, you know, it's good old chemistry. And the one in corn is particularly bad about making zinc unavailable. Well, maybe that won't make any difference because maybe we can't afford to feed corn. But there's a whole bunch of other things like DDGS, we may not know what it does. Thinking about that its component is going to be primarily corn. We know that in the absorption process that there is a binding of the zinc to the sulfur and the nitrogen that are provided by amino acids. We know that there's a tremendous amount of competition in the lumen by iron, calcium, and copper. And all you have to do is go back and look at, go back and look at some of those papers, and you realize that, has anybody just paid any attention lately to how much iron is in a diet? I mean, look, there's huge amounts we bring in accidentally as a contaminant. What does that do with the zinc requirement? And does it change, I mean, today versus tomorrow because you're using different ingredients, right? You're doing least cost formulation. Okay, in zinc we know that it increases the synthesis, this is important, of metallothionein. We're going to talk about metallothionein. It is extremely important and probably maybe some of the keys about how we can begin to differentiate about zinc sources and providing for the animal instead of overfeeding. And the interesting thing is metallothionein prefers to bind copper over zinc. Now that's one of the interactions that's extremely important for how we end up, if we overfeed zinc, we end up with copper deficiency. In zinc absorption, if we talk about getting into the cell, we find that the zinc's going to be bound to either CRIP, which is a cytosine-rich intestinal protein, or to metallothionein. We showed this in our lab a long time ago. Marcia Carlson did the work. These cells are slopped. They're lost in the feces. And if you look at Mike Rinker's work, you can find out that the pig loads itself with zinc, and then we don't have the same amount of excretion. So you can control excretion by the amount you feed, but the first thing the pig will do is load itself. And I think we see this in some of the data I'm going to show you in a minute. We also know that zinc is involved in being able to cross, and it uses zinc transporters. This is a really hot area, and unfortunately for us in animal science, not many of us are doing it. The work is done primarily in rats and some in mice. But we have to go to school on those. We have to use them as sources of information. Okay. Oh, gosh. I know you guys can't see this, can you? I don't want to tell you to go to sleep, but that would be a bad thing. All right, go up to the top. Whoop. Go to the top up here and start looking. Okay. We're going to talk about zinc, and it's there with our protein, maybe coming in as an amino acid. If it's an organic source, it may or may not be. Okay. If we then look, and we're going with just the things we just talked about, we're going to have to take it away, we're going to hydrolyze it, and we're going to do this two places. We're going to do it both in the stomach, and we're going to do it in the small intestine. Okay, this is when you have your overwhelming, your pharmacological zinc that comes in, and it avoids everybody. It just comes rolling in. It avoids all the control mechanisms, which is important from the standpoint of understanding zinc need. I just cringe when somebody says, well, if you get a growth response with pharmacological zinc, that must be the requirement. Give me a break. It just means you can overwhelm the system. It's kind of like anything else. You know, we talked just recently about the resistance in bacteria. Yeah, we do things screwy enough, we can mess everything up, right? Okay. If we look here and we see that we're having on the outside edge of this enterocyte here, we have the ZIP protein, which is a transport protein that's going to take the zinc inside the cell. There's a control point there. Once we get it inside, we have the zinc inside. We just said you can either bind it to CRIP, the protein, or you can bind it to metallothionein, or it can serve a function, or it can go running right over. What did I just do? It's not showing green, is it? Or I mean, dreaming. That turned off? That'll be even crazier yet. I did turn it off. Okay, it goes over and it gets carried into the body, into the bloodstream by a transporter. There is a gob of transporters. You know, and they do things with different organs. We have to be talking about enterocyte here because we're talking about, you think I can do better with that one?
Good at that.
With two hands working, I don't know. Brian, you know me well enough. Okay. And let's get past some of this because we are low on time. Okay, so I just want you to think about the transporters a little bit. Come on. This also, okay. If you look down here, you can see this is the part we talked about where if it doesn't get absorbed, it doesn't go in here, then it can get, the reason it doesn't get absorbed many times is because it's bound to an oxalate, a phytase, a tannin or something. We don't worry much about tannins in the pig industry. And then we can have excretion occur. Transport in the blood, it doesn't like to run by itself. It always holds hand, and mostly with albumin, but it can be with some of the other proteins too. They're all important, and that's why we have to have the good nutrition of the animal. You cannot create requirements, distinguish what is going to be the need of the animal when the animal is not healthy in all phases. The animal has to be able to grow. And there are some really old literature that's really crappy because the animals weren't growing, and they established requirements based on that. Okay, inside the cell, you guys already know, zinc does all kinds of stabilizing things with DNA and RNA, and without it, we're in deep doo-doo. And people that have genetic disorders like the acrodermatitis enteropathica or anything like that, those people are in trouble if they don't get adequate zinc, as we would be. And I am concerned about people that are vegans, because one of the best sources of zinc that is useful to the human is pork, beef, chicken. I hate to admit it, but beef actually has more. Another reason why we need to be concerned is bone health. Not because we need gobs of it. This happens to be rat work, and the reason, I actually know I skipped the slide, but one of the reasons why we need to think this happens to be rat work, look at, this happens to be the trabecular bone in the tibia. And look at this is a low zinc diet. It's not a deficient diet. It is a low zinc diet for a rat. And look at the difference in the bone structure in these two. So if we don't get adequate zinc, and particularly I'm thinking about females we're going to keep back, we're going to be a part of the herd. I'm thinking about herds that do all kinds of things for multiplying the females. We need to be really concerned about the amount of zinc they get. Not too much, but an adequate amount. This is the pig I wanted to show you. This actually occurred in today's world. How many of you guys have seen parakeratosis? Well, more than I expected. But I had not seen the full blown until I saw this one. This happened to be Rachel Howdy-Shell, who's now Martin, and her paper was published in 2011. And this is a pig that has parakeratosis. This was done in a normal swine diet, a normal nursery diet where no zinc was supplied. In other words, that pig had to get the zinc out of the dietary ingredients. Obviously, it didn't. This is where we go too far. If you overfeed zinc and you continually overfeed zinc, this is this erosion that has occurred. This is a result of lack of copper. Remember I told you that zinc is preferentially stimulates metallothionein, but it likes copper better. There was not adequate copper. Now, these sows had been on this diet for a long time. It doesn't happen, but there are a bunch of people who, as we think about anti-antibiotic, as we think about natural and all this, that may be trying to feed large amounts of zinc for long periods of time. I put this in there because I want you to remember that there are risks. Okay, the study I want to talk about is a study that we did at Ohio State with Don Mahan. Jim is here representing the lab today. 500 nursery pigs. There were 6 diets. You got to kind of work with me on the slide. We either added 25, 50, 75, or 100 parts per million of either the organic, the Bioplex, or it happens to be an organic source. Would this whole thing happen with another organic source? I don't know. Would the whole thing happen with another inorganic source? I don't know. So I'm just presenting what we've got here today. Then we had 2 additional diets. We had either the 25, 50, 75 of the organic or inorganic, and then we had a basal diet where we did not add zinc, and then we had a treatment that was 25 parts per million of organic plus 25 of inorganic. The reason that's in there is because a lot of people will back off of an organic source and go, it's too expensive, but I'll feed a little bit, right? Some of you guys know that happens. And so we wanted to know if the response was the same. And this is probably what I'd call customer friendly for that reason. We collected performance data. We killed pigs 6 per treatment at 10 days and 8 per treatment at 35 days. And at that time, we collected a lot more tissue, but the tissue I'm going to talk about today are the liver, the duodenum, mucosa, and the jejunum. Never see the day Hill can't talk. If we look at average daily gain here, I think it's called classes start, and the students have to put up with me. If we look at average daily gain here, I want to walk you through this because the colors drive me nuts, and maybe you do better than I do. But average daily gain is on the vertical axis. It is done in pounds. The basal diet, we're going across this way now. The 25 of the organic 50 of the organic, 75 of the organic, 100 of the organic, 25 of the inorganic, 50 of the inorganic, 75 of the inorganic, 100 of the inorganic, and the combination. And if you look at average daily gain, statistics can't find any differences there. But I would begin to tell you that the pig already knows, and this is, by the way, this is early on, that the pig already knows that it doesn't have enough zinc for growth, and is probably conserving things. If we look at average daily feed intake, there appears to be no difference, but you guys know better than I do that it doesn't take much difference in feed intake to make a big difference in cost. And if we look here, we will see that there appears to be a little bit of difference. Our combination is kind of holding in pretty well with the others. This is gain to feed, and I know Gary Cromwell just fell off the chair because he can't stand gain to feed, right, Gary? He wants feed to gain. But anyhow, the basal is definitely showing up here as not doing well. Now, here's the nitty-gritty stuff we're going to get now, and be patient with me, you guys. We're looking here at 10 days. We killed pigs at 10 days post-weaning, and these pigs were 18 days old when we weaned them. So this is 10 days post-weaning and 35 days post-weaning. This is the concentration in the diet, which are represented below here. This is liver zinc concentration and liver metallothionein. Now, if I would have given this presentation to you 5 years ago, and I hadn't had any, well, probably more like 10 years ago, and hadn't had as much interest in metallothionein, I would have expected that these two would mirror image each other. Because we said, right, a whole bunch of the zinc goes, and it's in metallothionein, and it's in that enterocyte, and then it gets picked up and goes to that liver to do its job, right? It might be storage, or it might be just doing a job there within the liver. They don't look alike at all. These two graphs don't look alike at all. If you look, you can see that our basal diet is already showing less, but not as bad as you might think when you compare. Who's this character that's out here? We're finding out that the combination did better in this case than the 100 of the inorganic. I would not, now this is storage, or maybe for usefulness, we don't know. However, on metallothionein, the thing that comes out really clearly is, and we are at this point talking about the liver, look who's coming up here tall. It's 50 organic. Would not have expected this. If we now look, we're looking at 35 days. These animals have had an opportunity to absorb quite a bit more zinc. And if we look, this does not look, I'll just give you the quick look back. They don't look alike at all, right? 10 days and 35 days. Now that's not that many days, but look at the change that's occurred. And if we look at storage, which we would assume, we would find out that probably these are somewhat similar statistically. But if we look at MT, it is just plain crazy. The metallothionein does not mirror image this at all. Our basal is really hurting because it doesn't have much zinc to store, and it doesn't put it in a metallothionein form. If we look at the combination on the end right there, it is really not at all like what our better organic and inorganics are. If we now look at the duodenum and the jejunum of the mucosal cell, the duodenum is here. Now, which one did I tell you guys where all the absorption occurs? Duodenum, right? It's where the first part, the proximal part of the small intestine. Look at that. Look at all of the amount that we have here showing up of MT compared to the jejunum. And if you think about, think about that image that you tried to look at, you think about how the MT was holding that zinc. It was holding that zinc so that it could be done something with. It could either be a cell function or it could be taken over and be transported. MT was sort of like a protector, a storage protector. And look at the differences we see here. MT in the duodenum is much, much greater than the jejunum. That just reinforces what I've been telling you. Now, if we look at these, there actually is a statistical difference here. Probably doesn't surprise you too much. Let's go through them again. This is the basal, this is 25 organic, this is 50 organic, 75, 100, this is 25 inorganic, 50, 75, 100, and this is the combination. Really, really. So it's saying that this is being held there so that it can become a useful function if that's what it needs to be, or it can be transported out of the enterocyte. That was at 10 days. This is at 35 days. The picture is somewhat similar. Again, the main thing I'd like to point out is certainly the jejunum is doing nothing here, nothing good anyhow. But it's interesting to me that the basal is just about the same as the combination. Wouldn't have expected that one. All right, in summary, and we're still late, but a little closer. The nursery pigs do not manage the organic and the inorganic zinc in the same manner in this study. This is Bioplex zinc sulfate. You could be using oxide, you could be using a Novus product, you could be using lots of others. We cannot assume everybody's alike. They are not alike. So that's the first disclaimer I have to give. The second one is here, the organic zinc, the initiated absorption of the zinc by increasing the amount of MT in the duodenum, and that 10-day picture that was radically, really interesting and radically not expected here. And I think that if we look at trying to quantify exactly what the requirement is, not overfeed and not underfeed, because I showed you why, that we have to be cognizant of things like this. We have to be looking at transporters, metallothionein. We can't be looking at how much zinc is stored in the liver. MT has the potential to hold the zinc for binding to the carrier. That's extremely important. And because of its role in zinc absorption, the amount of MT protein in the duodenum is twice as high as the jejunum. It's an important thing to think about when you read papers. What really cracks me up, you guys, you get a paper to review, and they say they looked at intestinal something, and they assume they have the difference between the duodenum and the jejunum, and what they did was they went in and cut the first X number of centimeters. They have no clue. They didn't look in the microscope to see what kind of cells they had. There is a big difference. My conclusion from this is the modern pig, the amount of zinc that's required for the high lean genetics we have today in the nursery is below what's currently recommended by NRC. Granted, in '98 they had no opportunity to look at this kind of data. We didn't have these kind of tools that we have, but I think it's something we need to think about, and I know at least some of my colleagues and I have talked about what it is, and can we go lower, should we go higher in a lot of minerals. I challenge you all to think about dollars and cents and savings in getting the good data to make your recommendations with. Thank you, and I will answer questions if Brian will let us.